Welcome to the first Provost Distinguished Scholars Lecture for the spring. You know, for millions of people in Haiti of Haitian descent around the world, January 12th, 2010 will be a date in history for them. Because on that day, you had a phenomenon that changed the lives for many, that ended the lives of many, and that will mark a new kind of status for Haiti and for Haitians around the world. And as we at the college thought of how we might respond to that date in history, we remember at all times that we are an educational enterprise, and that phenomena, whether they are natural, political, or social, phenomena always present teachable moments. And we wanted to make the Haiti event a teachable moment in many respects. And partly because the Haiti earthquake has a base in science, has a scientific explanation to it, we thought that we wanted to make this distinguished lecture a teachable moment regarding the science of earthquakes. And as I thought of people who I know to be experts in the field related to work in the Caribbean, I thought I'd invite a colleague and friend of mine from Florida International University to help us have that conversation, to help us have that teachable moment regarding the science of earthquakes, not just in Haiti, but in other parts of the Caribbean. Remember too that many of you may not have heard of earthquakes in the Caribbean, but Haiti is not a singular, solitary event. Any Jamaicans in the audience? Any Jamaican descent? Well, if you ask a Jamaican student, even if he was not born in Jamaica, what's the capital of Jamaica? He'll tell you Kingston. But then, if you ask him, has Kingston always been the capital of Jamaica? He will tell you, or she will tell you, no. It was a natural phenomenon, an earthquake, that changed Jamaica's decision about where to have its capital in 1692. So earthquakes are not new to the Caribbean. It happens that there are particular reasons why Haiti, January 12, 2010, presents a specific challenge for many of us, but it's always important to keep the context, and Professor Grenville Draper will help us understand the context, will help us understand some of the science of it. I'm not going to introduce Professor Draper. I simply wanted to welcome you to this event and to encourage you to make this a fully maximized teachable moment. My pleasure now it is to introduce Professor Nas Kandaka from our Department of Earth and Physical Sciences to introduce Professor Draper. Thank you.
Thank you, Provost. It's my honor and great privilege to come to the podium and invite you to attend this distinguished lecture series. As part of the lecture series attendees, you will also become distinguished today. Now, I'd like to introduce Dr. Draper. When I was looking at his CV, I don't know where to begin. It was some outstanding record of scholarly teaching, service, combination of all other stuff. So what I did, I just summarized some of the highlights from his CV, and I'd like to inform you about his accomplishment throughout the long 40 years, close to 40 years of teaching. Professor Draper comes from England, Leeds, Yorkshire. I believe I did it right. Mm-hmm. He's a great fan of cricket, just like the West Indies. However, when he received his PhD from University of West Indies in 1979, the World Cup Series, the Prudential World Cup Series cricket match, West Indies beat England at the time. So that could be a little irony there. Prior to getting his PhD from University of West Indies in 1979, he received his master's from the Imperial College, London, and his bachelor from Cambridge University. Then he came to the United States to teach at Florida International University, and he has been teaching at that institution since 1979. So it's almost 40 years of teaching at Florida International University. Now, his background is a mixed blend of scholarly service, research, as well as a public commentator for relaying science to the general public and also to the community people. In 1991 and 1994, those are the 3 years, he was the chair of the Department of Earth Sciences, which recently became Department of Earth and Environment. His expertise primarily is on the Caribbean geology. In geology, what we call hard rock geology, nothing to do with the recent hard rock music. So, but it might resonate from his talk. Dr. Draper supervised many graduates towards master's, leading to PhD. His scholarly experience include almost 70 refereed publications, almost 100 meeting presentation in national meeting. He was elected to the Fellow of the Geological Society of London, a great honor bestowed on him by the London Geological Society. Besides teaching, he supervised the Geology Club continuously from 1986. And I believe this will be the longest track for a faculty member to supervise the Geology Club in any institution. He is always relaying geological concepts, geological phenomena to the public forum. He published many articles in Miami Herald, informing general audience about the significance of the earthquake, environmental pollution, and so on. He also represented the Department of Earth and Environment in local news media. He appeared many times, provided commentaries on many geological issues. So a person with multiple intellectual, scholarly, and research capabilities. Without any further delay, I'd like to invite Dr. Draper to the podium. Please welcome Dr. Draper.
Well, thank you for the opportunity to talk to you here. This is my first time back in New York in about 20 years, so it's actually very nice to return. And I don't know who the person Dr. Cantico was describing, but it's certainly not me. Let me do this without having my back to you, but it's a little tricky shooting over my shoulder. Okay, this. I decided to entitle this talk, It Tore the Rock and the Mountains. And that's actually a quote from an eyewitness of the 1692 Port Royal earthquake that was mentioned by your distinguished Provost just now. And I think as a dramatic phrase for the non-scientists, I think it does convey something of the awesome power that lies behind these large earthquakes. Could I have the next slide, please? So this is it's an anonymous account of the Port Royal earthquake and a letter that was sent to England. And I start with this earthquake because it's really the same fault system that caused the Haiti earthquake, and it has the distinction of being the first earthquake that was whose time of occurrence was accurately recorded, and that was at 11:43 a.m. On June the 7th. The next slide, please. This is a small map of Port Royal. What happened was that this section of Port Royal, in the shaking of the earthquake, the wet sand that was really the basis of Port Royal liquefied, so it turned in an instant. The shaking just made it act as a liquid, and it slid off into Kingston Harbor. and took a large amount of the town with it. Now, some of the gentlemen, this was a haunt for pirates, but some of the gentlemen had pocket watches, the early pocket watches, or they'd stolen the pocket watch from somebody. And so we know the time because the various clocks and watches that slid into the harbor have later been excavated, and they all show the time as being 1143. So it's one of the first historical earthquakes that we know sort of to the minute when it actually occurred. Next slide, please. This is a contemporary woodcut of what was happening. Here's a lot of people drowning in the harbor and the houses turned over. And this is supposed to represent a circle of people praying because they were really shaken up, I mean, no pun intended, by this event. And really caused a great deal of destruction. And as your provost said, it encouraged people to move the capital from this spit of land, which is Port Royal, to what is now the present capital of Kingston. Next slide, please. So then this is, now this is what wasn't the only earthquake that has affected Jamaica. 1692 was we think was a very large earthquake, but we had another large earthquake in 1907, and this caused some destruction of buildings. This is a contemporary photograph. And then there was another one in 1957, and this is at Port Royal. It's called the Giddy House for obvious reasons. You can see the liquefaction has occurred again, only this time the building hasn't broken apart, and it stands there today as kind of reminder of what can occur there. Next slide, please. Okay, so that's by way of introduction, but let's get down to what actually are earthquakes. Well, when you experience an earthquake, it's a bit like being in a boat on the water and on a quiet pond, and somebody drops a large weight into the water, or somebody disturbs it. And in this case, we have a drop of water entering a small pool here, and the energy of that impact causes waves to carry the energy away from this in circular motion. Of course, if you were in a boat, you'd feel the boat rocking. It would rock for a while, and then it would calm down again. So what we have in an earthquake is the same thing, but waves occurring transmitted through a solid. In this case, what we call elastic waves. Next slide, please. Now, things that can cause earth tremors or earthquakes are, we've all experienced probably the ground vibrating from the passage of a heavy truck. If you've ever been close to a quarry when they're blasting, you would again experience a tremor. Landslides can also cause tremors. Even visitors from outer space can cause large meteorite impacts. But the most common cause of earthquakes in this planet is motion on geological faults. Next slide, please. Now, faults are really planar features that separate two blocks of rock in the earth, and they're fractures on which sliding has taken place. And so these faults can either move past each other in a very slow motion, a process that is known as fault creep, but often, more often than not really, the fault sticks. It's held by friction, and then the stress builds up until the friction can no longer hold it, and then the fault slips in a very rapid motion. And that's really what, essentially what causes earthquakes. So next slide, please. There are different kinds of faults, three basic different kinds. Normal faults in the earth correspond to extension within the earth's crust. Compression causes a kind of fault called a thrust fault, where one block of rock is pushed up over another. And the compressional situation can also cause what we call strike-slip faults, where the motion of the fault is sort of horizontal, parallel to the Earth's surface, and essentially is sliding by each other. So this illustrates the different kinds of faults. This is the normal fault. One block slides down the fault plane. This is the fault plane. In dip slip faults, also known as the reverse faults, one block is pushed up over the other. And then in the strike slip faults, one fault slides past each other. Now this is the kind of fault that caused the Haiti earthquake, this strike slip fault. And I never thought I'd be talking about another earthquake, but this kind of earthquake, this kind of fault is what caused the Chile earthquake just this last weekend. Next slide, please. So this is what a fault looks like. It is a plane, but it sort of goes into the rock here. And if you look at this carefully, you can see these horizontal layers of rock in here, beds as we call them. And if you follow this up here, you'll see you can pick them up there. So we know that this is a normal fault. This side has slid down with respect to this one. Changing them rather quickly. So what actually happens in this process where the fault sticks? Well, we'll do it for a strike slip fault. This is the fault plane here. And then this is a marker line. And so because of the motion of the Earth's lithospheric plates, that's a long word, I apologize for using it, but it is the correct word. In geology, a professional geologist would not use the term tectonic plates. That's a giveaway. You're an immediate amateur if you use that. It's like using, I showed you those layers, those are beds. If you say strata, thinking it sounds more scientific, no geologist ever uses that word. So the strain builds up. Next slide, please. And it deforms the rock on either side of the fault, but the fault stays together. And this can go on for years, months, well, years, centuries even, as we've seen in the case of Haiti. And then, but at some point it will slip. Next slide, please. And then in one moment, that fault slips. In the case of the Haiti earthquake, that displacement was about 2 meters in a fraction of a second. This little diagram down here, I hesitate to put this in, it's a little bit technical, but these are generated from the earthquakes when they arrive at the detecting stations, which I'll talk about in a minute. And this tells us that it was, in fact, a strike-slip fault. This is we call it the mechanism from the Haiti earthquake. Next slide, please. So again, that's the amount of slip that's occurred. Next one, please. Okay, to show you a real example of that, this is a contemporary photograph taken in 1906 from the big earthquake in San Francisco. That also was a strike-slip earthquake. The San Andreas Fault, the world's most famous fault, is a strike-slip fault. And you see this is the fault trace, as it's called. That's the fault line. People talk about fault lines. That's where the fault plane meets the surface of the Earth. It should be more correctly called the fault trace. So the fault ran through here, and then in the earthquake, the fence was offset by about 2.5 meters, or what's that? It's about that was a magnitude, estimated to be a magnitude 8 earthquake. We don't really know, because it was really before they had the instruments to measure these. And so that's comparable to what happened in Haiti. Next slide, please. Okay, so just to recap, we get that slip occurring beneath the ground. The place where the maximum slip occurs is this region. The break in here is often called a rupture. So that's the focus, and the geographical position above that focus at the surface is called the epicenter. And then when that slip occurs, we get the radiation of these waves from the focus of the earthquake. Next one, please. Now, let's look at those earthquake waves, because it's in trying to understand what happens in an earthquake, we have to examine this. This is, there are 3 kinds of waves that are produced in an earthquake. There are the P waves, which are the fastest moving, and the P waves travel at 8 kilometers per second. There's a second set of waves that are produced called S waves, which travel somewhat more slowly at 5 kilometers per second. And then we have the surface waves, which travel more slowly, 3 to 4 kilometers per second. And these are actually the ones that do the most damage, because these are actually on the surface of the Earth, and it's the vibration that really will just break a building apart. Next slide, please. Okay, so what are these different kinds of waves? So this, the P wave is really a shaking that's back and forth in the same direction that the wave is traveling. Now, has anybody here ever played with a slinky? Yeah? Just yesterday, right? And so if you stretch out your slinky and you chug it back and forth at the end, you'll see these compressional waves, P waves, move along the fault. The S waves is more like taking the slinky and just shaking it from side to side. So there's a sideways motion. The vibrations are perpendicular to the direction of motion of the wave. Next slide, please. And then there's the surface waves. Basically two types. A Rayleigh wave is the one you're familiar with on water. That's an up and down motion. But there's also a side-to-side motion, which is known as love waves, really. They're named after a physicist whose last name was Love. Now,
Are you sure about that?
yeah, absolutely. Now, in these, if you have a very large earthquake, in this up and down motion, sometimes you can get fissures opening on the crest of the wave. The Earth is flexed so much by a very large earthquake that a fissure will open. There have been cases of people actually falling into these. And Charles Darwin wrote about this on his voyage on the Beagle around the world, and he actually witnessed an earthquake at Valparaiso in Chile, another large earthquake, and he describes how there was a donkey that was standing there. The fissure opened up underneath the donkey fell into the fissure, but then the fissure closed it back over the poor donkey, leaving only its ears sticking out of the ground. Yes, read Darwin's Voyage of the Beagle, it is described there. Okay, next slide, please. Okay, so the next thing is, well, I mean, we can detect earthquakes by experiencing them, but scientifically, how are we going to examine earthquakes? And a lot of what we know about this is from the detection of earthquakes using an instrument called a seismometer. Now, a seismometer is really not a particularly sophisticated thing. It's basically a frame from which is suspended on some springs a fairly heavy weight. And the idea is that as the ground moves up and down, then the weight stays stationary and the frame moves. And if you've got some kind of recording device, in the old days they used these rotating drums, and the weight would trace out the vibrations of the earthquake on the drum, and then you could just peel off the paper from the drum and examine it in more detail. This is a different design for looking at horizontal motions. Now, these days we don't use the paper drums, we use electromagnetic detectors, which then send a signal to an amplifier, which is then sent to a computer, and so we can then display that on a computer screen. Next slide, please. So this is what a seismic station actually looks like. This, believe it or not, is in Miami, Florida, where there are no earthquakes. And the reason it's there is that we do have a nuclear power station. And by federal regulations, all nuclear power stations have to have some kind of seismic monitoring equipment, whether in an earthquake zone or not. So this is the station. It's basically a concrete platform with a pillar cemented into the ground. This is a battery. This is the power supply, a backup power supply in case the power goes out. There's a computer there which processes the signals, and they're sent by telephone line to the University of Florida in Gainesville, who have the contract for operating this system. Next slide, please. This is a little bit more close-up here. And you see there are 3 seismometers, and that's because we want to detect up and down motion, north-south motion, and east-west motion. So there's 3 different things being recorded. Next slide, please. So when you take this information, you basically display them on your computer screen as basically a graph of time against the shaking. And because there is this difference of velocity of these waves, the P waves arrive first, followed by the S waves, followed by the much slower but much greater amplitude or height surface waves. And because there is this time difference, the time difference is a measure of how far you are away from the earthquake source. And the longer that the longer the interval between the P and the S waves, the further away is the earthquake. Next slide, please. So let's imagine we have an earthquake. Focus here. This is seismograph station A, B, and C, different distances away. The P-S wave interval at A is going to be much shorter than at B, and in turn, that's going to be much shorter than at C. So next slide, please. So this is how we would compare these things. We have the seismograms here. These travel time curves, as they're called, are established for each seismograph station. It depends on the seismic properties of the rock around the station. But you can then see how in seismograph C, the P-S wave interval is much greater, and that means it's much further away from the source. Next one, please. So then it's a simple matter, and then on the map, you know the distance that this was, and you just basically draw a circle around A. That's telling you it occurred somewhere on that circle. You draw a similar circle around B, then you get two possible places where the earthquake could be, and then C is the tiebreaker. You realize it's there, not there. And that's how we determine where the epicenters of earthquakes are. Now, in the modern day, all this information is radioed back to, or probably using the internet now, to the National Earthquake Information Center in Colorado, which is operated by the US Geological Survey. They have various agreements with seismic networks all over the globe, and they bring it together in one place. It's really an excellent resource as a website. If you just Google NEIC, National Earthquake Information Center, that'll be the first hit that you get. And then anytime an earthquake occurs, you can go and have a look and see what its characteristics were. Now, what you'll notice if you visit that site is that earthquakes are occurring every day in different parts of the world, and most of them are actually small. The very smallest ones, the NIC doesn't bother to handle, but it will show in bold letters anything over magnitude 5, and I'll talk about magnitude in a moment. Next one, please. This is the seismogram, as it's called, from, there was a P there, which has disappeared. How did that happen? But this is the P wave here. This is recorded at the seismic station in Mayagüez, Puerto Rico, and was sent to me by an ex-student of mine who's working there right now. So this is the P waves here. This is the S waves, and then this is the surface waves. Now look at the size of the surface waves. It's actually what we say, we saturated the seismometer. It can't show the full shaking. And of course, Mayagüez is in western Puerto Rico. It's fairly close to the earthquake. Next one, please. Now, so if we locate earthquakes, and all over the world, by this worldwide seismic network, we can plot these on a global map and see where they occur. And what we see over this almost 40-year period is that earthquakes don't just occur anywhere. They occur mainly in these narrow zones. And it was this discovery that led to the theory of plate tectonics, where we now realize that where all these earthquakes are occurring are the boundaries of large plates on the Earth. And where they're rubbing up against each other, that's where the earthquakes are generated. And these plates just move continuously at a couple of inches, well, anywhere from about an inch to, say, 8 inches per year. So I'm trying. So that's incidentally this setting up of the worldwide network was not done for scientific reasons. It was done because of the Cold War and nations wanting to monitor underground nuclear testing to make sure that people were complying with the treaties. So it's really actually paid for by defense departments. But the useful thing that comes out is we see there are these seismic zones here. So we see here in the Caribbean that there are lots of earthquakes, and they define the Caribbean plate, which is trapped between the South American plate and the North American plate. And the earthquake in Chile the other day was due to the interaction between the South American plate and this plate called the Nazca plate, which is one of the plates that makes up the Pacific Ocean. Next one, please. Now, this slide stayed in from a talk I gave last week, and I knew that there were going to be a lot of math students in the class, so I decided to keep the equation in. Don't worry about it. Basically, the magnitude, we use the seismometers to determine the magnitude, and it's related to, it's actually derived from looking at the maximum amplitude of the surface waves and the time at which the maximum amplitude occurs after the first surface wave arises. I know I'm getting a bit technical now, but it is actually, it's been shown, it can be demonstrated, mathematically proved that it is related to the amount of energy released at the site of the earthquake. So the magnitude, which is the m there, is basically related to the energy released by this equation. Now, so in other words, magnitude is a measure of the energy release of any given earthquake. But look, we've got a logarithm here. This magnitude is a logarithmic thing, which means that when you go from, say, a magnitude 5 to a magnitude 6, and a magnitude 6, you have 10 times the amount of shaking compared to a magnitude 5, and 33 times the energy release. Next slide, please. So, if we look at magnitude and energy, this graph, I hope you can see it from the back, because some of this is a little small here. This shows a number of different things. First of all, it shows you the number of earthquakes per year of a given magnitude. So you can see that there are over 1 million earthquakes of magnitude 2 earthquakes. You get about 2,000 magnitude 5 earthquakes per year. But as we get up to the bigger earthquakes, they are much rarer, fortunately. The Haiti earthquake with magnitude 7, you can see here, is comparable to an earthquake in Charleston, in South Carolina, the Loma Prieta earthquake in California, and the Kobe earthquake in Japan in 1995, and just a bit more powerful than the Northridge earthquake. So it's a pretty powerful earthquake, but there are ones that have occurred which are greater. The greatest ever was a 9.5 in Chile in 1960. For comparison, there's some other things here. The eruption of the supervolcano Krakatoa is here. This is the energy released by the Hiroshima atomic bomb. So what hit Port-au-Prince was really something greater in terms of energy than a nuclear device. Next slide, please. So this is the Caribbean, and this shows it's from my colleague Eric Calais at Purdue, who works in these in Haiti. And each of these show earthquakes over the last few years. The greater the circle, the larger the earthquake. And you can see there was a small one in Jamaica a few years ago, and you can see these other ones here in Hispaniola. Note the two zones in Hispaniola, one in the south where Port-au-Prince is, and one in the northern part of Hispaniola. Next slide, please. Now, these are due to the plate tectonics of the Caribbean. Basically, the Caribbean, the main Caribbean plate is this region here, but it is broken up into what we call microplates. It's rather complicated, And one of these in northern Hispaniola is the Gonave microplate here. This is the Puerto Rico microplate. And then we have something here called the Septentrional microplate. And the two major fault zones that affect Hispaniola are this one that comes all the way from Jamaica, responsible for the 1692 earthquake, cuts right through the middle of Jamaica, as you can see, right down the southern peninsula of Haiti, and then we kind of lose it as it goes offshore in this region near the Muertos Trough. And there are some other microplates down here in northern South America, but we're not concerned with those today. So we are concerned with these two zones here, the Septentrional fault zone and this one. So you can see this goes very close to the capital city of Kingston of Jamaica, a large populated area, as well as Port-au-Prince. So this is potentially very deadly. Next slide, please. Now, if we actually look at the depth of earthquakes, and this is a weird kind of diagram. This is as if you were in the earth looking upwards. So there's Hispaniola, and there's Puerto Rico, and you can see there's actually two sets of hypercenters. That's the place where the earthquakes occur. And this is another complicating factor, because what this means is, next slide please, is that this is the northeastern Caribbean, and Puerto Rico and Hispaniola kind of sit on this zone where two plates are converging towards each other and actually touching each other. So there is a potential not only for the strike-slip kind of earthquakes, but also for the thrust-type earthquakes, which is similar to Chile. Next one, please. Okay, so a geologic map of Hispaniola that I produced some time ago. And I've superimposed the faults on here so you can see where they go. And you see the question mark here. We don't quite know where this one ends. And then there's a septentrional fault that comes through here, which is also has the potential for seismic activity. Now, strangely enough, I spent my Christmas vacation down here because my wife is from the Dominican Republic. And we actually did a tour of this area known as Lake Enriquillo, and I actually came very close to the Haitian border there and actually crossed the fault. And little did I know that, that fault would be very famous 2 weeks later. Next slide, please. Okay, this might be a little difficult to read from the back, but I'll try and walk you through it. These are what we call the rupture. This is the extent of the tear on the fault for historical earthquakes. So we certainly know that these have occurred in the past. And look over here, we had two earthquakes, one in 1751, another in 1770, another one over here in 1751. So it's really a dangerous zone. You can see 1692, 1907 here in Jamaica. And then we've got this other zone here that goes along the north. The 1842, there was one in 2003 in this region, then a whole cluster over here. The worst of these was in 1942 when a large earthquake occurred here. And this was an earthquake on a fault that's underwater, and it displaced the ocean, and it caused a tsunami that struck a town called Nagua, where more than 2,000 people died. In fact, some people say at that time the Dominican Republic was run by a notorious dictator, and there's some talk that he may have suppressed the amount of casualties just for his own ends. So there's plenty of historical evidence for realizing that this is a seismically active area. Next one, please. This kind of pretty much shows the same thing. It shows some other ones here in Central America. This is a bit easier to read, though. The important ones are 1770 and 1751, which occurred in this area. That's the crucial aspect. So that was over 200 years ago, but they were large earthquakes, and they did destroy. Port-au-Prince was much smaller then, much less population density, but did destroy the city. Next one, please. And again, yet another one, historical earthquakes. It's sometimes actually difficult to guess the size of historical earthquakes because there were no seismometers around. And again, we see the same pattern here. And you can see the mainly two areas here and here, but there are some that occur in the center of the island too. Okay, next one, please. Okay, so let's get back to some modern earthquake science. One of the things that's really helped us understand the way that plates move and the way that the ground moves around these seismic faults is using the global positioning system. This is the same technology that if you have one of those GPSs in your car that gets you, I imagine very useful in getting around in New York City, but we can use these. We use a different type that's much more. We can get much more accurate motions. But if you occupy a survey point like this and you come back a few years later and look at it again, it will have moved a few centimeters because these plates are continuously moving. And so there is a seismic network station that's been set up in Hispaniola network over the whole island. Next one, please. Next one. Hello? Next slide, please. Yeah. This just shows the ones that my colleague Eric Calais has set up in Haiti. So he has these stations all over Haiti, including a tight cluster around Port-au-Prince here to kind of show how this is, how the motions will be taking place. Next one, please. Now, this is an early study when there were only 3 seismic stations in Hispaniola, but I think it makes the point. These yellow arrows are the rate of motion, and this is for scale. That's 20 millimeters per year. That's just over an inch per year. And these are the motion with respect to a stationary North America. So you can see that Hispaniola is moving eastwards with respect to North America, and you can see that it's only moving a little bit slowly here. It's moving faster here. That means there's got to be some differential motion between this point and that point. And then equally, there's some motion. This is greater motion with respect to North America, saying that there's motion between central Hispaniola and southern Hispaniola. Okay, next slide, please. Now, it's a little more difficult to see in this slide, but this shows the results from the whole set of these GPS stations that are around Hispaniola. You can see this general east to northeast motion of Hispaniola, but you see the gradient across Hispaniola. So Hispaniola is absorbing some of that motion. And in doing this study, it was discovered, finding the rate of motion across this fault, that they estimated it to be a few millimeters per year. And then they said, well, the last big earthquake occurred in 1770. That's 2 meters of motion. So that's 2 meters of potential slip on that fault that could happen. Next one. Next slide, please. This is the paper that was published in 2008 and was announced at a conference in Santo Domingo that I organized. And you probably can't see this from here, but so I'll read it out, is that similarly, the Enriquillo fault in Haiti is currently capable of a magnitude 7.2 earthquake if the entire elastic strain accumulated is released in a major event. So it wasn't so much that the earthquake was predicted, but its potential certainly was. Next one, please. And that's because there's an empirical relationship between, I know it's a log-log graph, but I am a scientist, I have to do this. But this is the distance in meters, and if you translate this across here, there's a relationship between the magnitude and the amount of displacement. And that's how they actually predicted this 7.2 earthquake. But it actually turned out to be 7. So probably not all of the strain has been released. Next slide, please. And this is a question I was asked a lot after the earthquake. I didn't know there were earthquakes in the Caribbean. Well, if you've lived there, you will have felt a lot. This is the annual frequency. So you find that there are a lot of small earthquakes. But these are not going to get reported. But the large earthquakes occur very infrequently. And so this is the problem. The plates are moving, in California, the plates are moving fairly fast, and they get they get a lot more of these intermediate earthquakes, and they're always reminded that, yes, we live in earthquake country. These large events in the Caribbean occur historically, as we see, but on a daily basis, you would not feel most of the earthquakes, and you might only feel a little tremor from time to time. So the reoccurrence interval, if you like, is large in the Caribbean compared to, say, California. We're talking about 2 centuries between these large events. Next one, please. And then, so after the earthquake, then this is it. Probably estimated the energy release equivalent to a 5 megaton bomb. And you can see the damage that all this has done. Next slide, please. Now, a lot of this was, next one, please. A lot of this was probably due to the fact that there's really no inspections, no building codes in Haiti. A lot of the construction is informal. But even a major building like the Presidential Palace, this was before, then look at the damage done to even a well-built structure. And that's because the earthquake, the epicenter of the earthquake was very, very close to the city of Port-au-Prince. So the energy was very, even though it was a magnitude 7, not considered one of the larger earthquakes, but if you sat right on top of it, as they were in this situation, then that concentrated energy is just going to cause a huge amount of damage. Now, there were some buildings that were built properly. The US Embassy is one, and the Digicel building, and they managed to survive with only minor damage. Okay, so this is, next slide, please. Now, using a technique in the United States Geological Survey produced this diagram where they showed, thank you, where they calculated the amount of stress release that occurred in the earthquake. So you can see the blue area means reduced stress, and that's where they thought the rupture was. But that tends to take the stress off the main fault and concentrate it at the ends of the fault, and those are the red areas. And these are some of the aftershocks of the earthquake, and you can see, of course, that the aftershocks are occurring in that area of high stress. So this is a technique that can help us understand where the aftershocks are going to occur. Next slide, please. Now, in terms of looking at the impact of this earthquake, this is a graph which shows deaths per earthquake versus the magnitude. And you can see generally there's sort of a trend, but not much. But the thing to note here is that the Haiti earthquake, the loss of life in this is much greater than any other magnitude 7 earthquake that we've had. And that's, again, a reflection of how close the earthquake was to Haiti and to the capital of Port-au-Prince, and also the kind of construction. A lot of these magnitude 7 earthquakes occur in places where earthquakes occur frequently, and so that's that constant reminder that you've got to maintain building standards. Next one, please. This is the modified Mercalli intensity scale. This is used when analyzing after earthquakes to talk to people, and they report what shaking they felt, and it gives you a way of mapping out the shaking on the ground. And I've highlighted these here as basically showing the ones that I'm going to show on the next map. So magnitude 6 is felt by everybody, and people run outside. Intensity 7, less damage. But then we get up into 8 and 9, and that's considerable damage in specially designed structures, buildings shifted off foundations, ground cracked suspiciously. So look for these in the next slide. And you can see that really some of the greatest shaking, the 9 shakings, are in this area actually to the west of Port-au-Prince, although they experience intensity 8 shaking, as you can see within Port-au-Prince here. And this is the fault that caused the thing, and this is where it probably broke. Now, the fault can creep, and eventually you will get a ground break, but they were not able to find one in this situation. So that means there might still be some stress left in this area. Next slide. This is a technique, I don't really have time to explain it, but it's using satellite technology, using radar from satellites, and you can measure very carefully the height of the ground. And then you can fly the same satellite over there again, and if there's been any changes in the ground level, you will get these what are called interferograms. And you can see that where that shaking was in here, there's a lot of deformation of the ground. So again, that suggests that that the rupture probably was terminated about 2 to 4 kilometers beneath the surface, and that there's still probably some stress built up in that area. Another large event maybe somewhere else on this fault, either to the east or even to the west of that fault. But really, the big risk, in my view, is this septentrional fault. Now, there's been some studies on this fault using a technique where where the fault cuts through river gravel, you can dig a trench with a backhoe, and you can see if there's been any displacement of the layers in the gravel. That gives you a measure of the earthquake, and then you can use radiocarbon dating in some of the layers to bracket when that event took place. And this work has been done in Hispaniola, and the septentrional fault last moved 800 years ago, and when it did, it was probably a magnitude 8 earthquake. Now, the great danger now is if that moves tomorrow, there's 800 years worth of strain built up in there, and it's probably likely to cause a very, very large earthquake. And this is where it gets personal, because my mother-in-law and one brother-in-law lives in that region. But then I have other brothers-in-law in Santo Domingo, and as you can see here, we had a large earthquake in 1751. This is a thrust earthquake, we think, something like the Chile earthquake. Those thrust earthquakes tend to be very large. So that's it. Unfortunately, I don't have a rather pessimistic view. The take-home message is basically we're going to get big earthquakes in Hispaniola again, but I can't tell you how big they'll be, and I certainly can't tell you when they're going to occur, but it is inevitable. But it may be another 100 years. Let's hope so. I think the final slide. Yes, my chair made me put this here. So if any of you are finding New York winters a little painful, and you decide that you want to come and do some graduate work, then you can get in touch with us there. So I'll be happy to take any questions.
Professor Schuler, Social Science, thank you very much for the presentation. I'm a social scientist. I do my work in Haiti. What you noticed about the time lag between, like, the California, it's slow but regular, so they can prepare, versus the time, the infrequency, but the severity of the earthquakes. There's a parallel between health, that people have malnutrition, which is more important than HIV/AIDS prevention. So some of what you're saying does resonate, but there's a disturbing trend that I'm seeing, that people get blamed for building houses where there's, like, high geological vulnerability. And as a social scientist, I just want to add to the conversation that Port-au-Prince was 500,000 people before an economic program called neoliberalism, and now it's 2.5 million before the earthquake. So I'm going back to Haiti in 3 weeks as an effort to rebuild the state university, and I'm going to be part of an interdisciplinary team. So what kind of questions should a social scientist be asking of someone of your caliber and some of your expertise as we think together about how to manage short-term risk with long-term risk? So.
That's a very good question, and it brings up a point that as cities the world over are getting larger and larger, people are concentrating in the cities. Many of these cities are in areas of high seismic risk, and as we've seen, with Chile, but Lima, Peru, our own San Francisco, Los Angeles. As we get these mega cities, then the risk of casualties gets greater and greater. In terms of now, Hispaniola is a region where there are lots of other natural hazards besides earthquakes. It's of course prone to hurricanes. That does in turn generate floods. and mud flows, and there's been some, in the last decade, at least two rather nasty events in Hispaniola that caused loss of life. I think that the way to go about this is to look at the total risk. If you can get geologists to, this has been done for some areas, look at all of the risks, look at the seismic risk, where it's most likely, you look at the landslide and flood risk and so on, and then you can build a composite risk map that might tell you the safest areas to be. Because when we had a teach-in on this at FIU, somebody suggested maybe the capital should be moved and they could go somewhere further north. And I pointed out that, well, only 2 years ago in the town of Gonaive, that was almost wiped out by terrible mudslide. So I think things can be done in this risk zonation thing, and at least it makes you aware of where you've got a high risk. It won't necessarily stop people from living there. People tend to have short memories and don't read history.
Well, I'm not just about short memories. People live in places that are high risk because they have no choice.
Yes, well, I mean, another thing I pointed out is that, well, it's all right talking vaguely about moving the capital, but if you're going to move a capital, you're going to have a large still a largish, if not, superpopulation center. You still have to have water supplies and so on. We had a conversation about this earlier, but there are historical reasons why Port-au-Prince is where it is, and one of those is availability of water, and so that comes into it. I mean, it's the same thing with volcanoes. I mean, people live on volcanoes because the soil is incredibly fertile, but there's always that risk, and from year to year, that's a good thing. But there's always that risk over decades that, then you'll be presented with a natural hazard. And just look at Seattle. I mean, I once had lunch on the Space Needle on one of the few days it's clear in Seattle, and as the restaurant came around, I could just see that there's Mount Rainier and there's Seattle Tacoma encroaching on the flanks of that volcano. That's going to be a big disaster sometime in the future. That volcano is going to blow one of these days. And also, I mean, speaking as a resident of Miami, we had short memories. We hadn't had a hurricane in 30 years, and then we were hit by Hurricane Andrew, and of course, we'd let our building codes and things become lax. So, I'm not sort of like blaming the Haitian people. They're just trying to survive, but they didn't know about the risk. Actually, they did know. I mean, the government did know about the risk, but they had lots of other problems to deal with. Yes, sir.
Hi, my name is Walter Jones. I'm with the Earth and Physical Sciences Department, and I'm an engineer and geologist by trade. My concern is the Pelegre Dam up about 25, 30 miles north of Port-au-Prince. It looks to be in a seismic zone, but as geologists know, what makes a good dam sites frequently also pertains to it has lousy geology. And the dam is infamous for not being well maintained at all and is very badly silted in right now. What you've just shown in your very, very outstanding lecture just now, and extremely well-researched lecture, is that there are, in fact, seismic concerns in between the Septentrional, I hope I pronounced that close enough, and the Plantain Fields Fault. That zone in there is not exactly pristine and pure as far as the seismicity is concerned. You've shown some earthquakes in there, and in the 1761 earthquake, it comes up and trends up into where that dam is, and I'm curious if you have some comments on the that middle less seismic zone in Haiti and the potential and the priority for putting this dam into some kind of repair. It's a fairly respectable sized dam, and it's not an earth dam. It's a concrete gravity dam, and I'd just like to hear what you have to say about that, sir.
There are lots of dams too in the neighboring country of the Dominican Republic, some of them very sizable and some of them very close to these zones. And you're right, faults, active faults tend to leave a notch in the landscape that often leads to where the rivers are narrow, and that the engineers think that's a great place to build a dam, but it's right actually on the fault line. And I can think of at least 2 dams in the Dominican Republic that are like that. Certainly, they already had a problem in a place called the Tavera Dam in the Dominican Republic when they had to let the water out a few years ago due to heavy rain, and a lot of people downstream got washed away. And that would be a sort of secondary effect of a large earthquake if any of these dams failed. I mean, it's potentially very serious, but at the same time, it's the balance between, you know, you need the dam for the water and the electricity versus, you know, when one of these events may or may not occur. So yes, they do present considerable danger, and maybe more attention should be paid to siting those dams so that they are away from what we know to be risky faults. Oh, sorry.
Hi. No problem. Kathleen Robbins, geology student graduating next year. I was
Yay!
I hope. I have a question for you. Is there any overlap or maps that have overlaps between the Coulomb stress and the interferograms, and possibly even overlap then with the microplates to see how the interaction between those?
Well, that's not something I'm really an expert in, but I understand your question. Those tools could certainly be used in making the seismic risk, seismic risk maps, which I think needs to be done. There's never been any real solid study making a seismic risk map for the island of Hispaniola. They did a very rough one for Jamaica, but not. I'm not even sure how good it is because it was based on, it was done a long time ago using older techniques, and things have come forward. But yeah, these are all tools. Now, these are very new tools, some of these things, and with the GPS, we're only beginning to see the payoff now, after about 10 years of measurements. And all the other techniques I showed, to be honest, I don't understand the Coulomb stress map, how it's generated myself, but they are things that obviously show a lot of potential for helping us understand, and we're not going to prevent an earthquake, but at least maybe knowing where the aftershocks are and then taking precautions.
Something to think about for a graduate project.
I'm sorry?
Something to think about for a graduate project?
Yeah, there you go.
Hi. I'm Stash, Life, Earth, and Physical Sciences. You were talking about the reasons why cities like Port-au-Prince are located where they are. Among those reasons being these deep alluvial soils, which provide productive aquifers. But we also know that those deep soils have a strong bearing on earthquake risk, and I wonder if you could comment for us on that.
Yeah, I really meant to mention that, but that deep alluvial unconsolidated gravel that we find there tends to have an effect, we call it the jello effect, of actually magnifying the shaking. So that's another reason why this disaster was so, or catastrophe I should say, was so intense, is that the earthquake was very close, and the magnitude of the and the shaking was exaggerated by this unconsolidated gravels. There's a problem here because that's the same situation in Kingston, Jamaica. And the reason that people settle on alluvial fans is that you can easily get water by just drilling a hole and you'll be able to pump water out of a well. It's always a good water supply. So people tend to congregate to these places because of the water supply, which is a day-to-day need as opposed to something that occurs every 200 years. But I worry about Kingston, Jamaica too, because if it hits there, if a big quake hits there, then it's going to be, the same situation. And people tend to build. A lot of domestic structures in Jamaica that they have concrete roofs because they're cheap to build and they don't blow away in a hurricane. but I don't know how well the rest of the building is constructed to keep that roof on if an earthquake occurs. Yes, sir.
Yes, I'm Carl Gomez from Global Medical. Can I say, you have to say if I'm correct or not, just the amplitude is to the intensity of the earthquake, what horsepower is into torque. Is that okay?
Well, no, the amplitude is the height of the wave, and the energy is related to the actual area under the wave. But I don't think it's comparable to torque.
You cannot make the relationship.
No, not really, I don't think.
Okay. My next question is a quick one. At what level on the Richter scale does the Earth become liquidy, like friable?
Even with small earthquakes, that can occur. It just depends on the ground conditions at a particular site. So it's not, obviously the larger the earthquake, the more likely it is to happen. But it's not strictly speaking related to the magnitude.
Are you familiar with the map of Haiti, like earthquake-wise?
Well, there's the ones I've shown.
Okay, hypothetical question. If you have to build like an Olympic stadium, okay, in Haiti, where will you put it? Thank you.
Okay, thank you. I don't know the geology of. I know the geology of Haiti only in a general sense. I'm much more familiar with the detail from the Dominican side of the island because that's where I do most of my research. But what I said about the alluvial gravels, it's been shown in many earthquakes that structures that are built on bedrock, as opposed to on these gravels, survive better because the shaking isn't amplified, and you know, so I would say building something like a big stadium, try to put it on somewhere that's going to be on bedrock. The only trouble is that for a stadium, you need like a fairly large area of level ground. That might be difficult to do.
Hi. I have a question on on prevention measures.
Mm-hmm.
What can we do for the local people to, in case they forecast a possible 7.0 on the Richter scale, what can the governments do of Haiti and Dominican Republic to save lives in case of these?
Okay, that's a very good question. First of all, they're not like hurricanes or even volcanoes. We can't forecast them or predict them. All we know is that the risk is there and that it could happen. What I would like to see, and I have concern for the Dominican side, is that the government has to have, just as we do with hurricanes, we plan. You have to have a disaster plan. You have to work it out. Earthquakes present different hazards than hurricanes. You can't use this. It's not a one-size-fits-all plan. You have to have one. And then when it's sort of a case when it occurs, which it will, then you've got to get the plan into action. And everybody has to know what their role is, and there has to be a chain of command. The Dominican Republic, for example, unlike Haiti, actually has a fairly large army that could be very useful in recovery from an earthquake. But there would have to be a plan, otherwise everyone's going to be running around and nobody's going to know what to do. It has to be worked out ahead of time, and it has to be rehearsed on a frequent basis. I think that's the best thing that it can do. The other thing that can be done is that really people have to take building codes seriously, and they have to be enforced, which unfortunately I know is not going to be true in either nation, and there's, you know, even with the best will, there's still corruption. And that's probably true of this country too. We won't know until a big earthquake happens in Los Angeles. But I think the best thing where governments do have a lot more control is over some kind of disaster plan. And, you know, it's been shown, certainly I've experienced this in Florida with the hurricanes, that when Hurricane Andrew hit, like nobody knew what to do. We learned from that, and now there are hurricane plans which are rehearsed every year, and supplies are stationed in certain areas ready in case something occurs. That's what, if this is what I want a colleague of mine who's a political advisor to the President of the Dominican Republic, that's the message I want him to whisper into the President's ear.
Round of applause for all of us.
Thank you very much. You've all been very gracious hosts, and I had some interesting questions.
When we have a tradition that whenever we have either a visiting lecturer or one of our own faculty giving a talk, we try to make it a Kodak moment. And we have a copy of the poster that you and I are supposed to say cheese at. And